Dear physics enthusiasts, today I want to talk about quantum teleportation. Since in my last video I explained what the Physics Nobel Prize of 2022 was about. It was mainly about the discovery and experimental demonstration of entangled photon pairs by one of the guys who received the prize was Anton Zeilinger, professor, an Austrian physicist from Vienna. And he also in 1997 could demonstrate in their labs that quantum teleportation works out. And this I want to briefly explain. It's not very simple, so it's more for the advanced people with an advanced physics background maybe, but I want to grasp you that you grasp the idea of how this teleportation works. So therefore I have prepared a little blackboard again, and the setup is the following. So this is basically the setup that the Zeilinger group in 1997 demonstrated: the teleportation of a quantum state set C1, labeled here. So this is a superposition of the polarization of a photon. This is photon 1, and this is then teleported to Bob's lab and the quantum state of C3 of this third photon here. So this is equal to C1 in the end after the teleportation was successful. So how does this work? Well, the central resource actually is an entangled photon pair. So this is what the Nobel Prize was about in my last video. So I don't go into the detail how you get these, but you need some special equipment in your lab, and then you can produce these two entangled photons. So this blue curved line should show the entanglement between the two polarizations of the two photons. So entanglement again here was the 100% correlation between the quantum state of a two-partite quantum system. In this case, two photons, 1, 2, and 3. Let's label them like this. And then you have the polarization here denoted by the arrows. And now this entanglement, for example, means if they are in a certain state, this means that if this photon is measured to be in a horizontal polarization, then the other one is with 100% certainty in the vertical polarization, or vice versa. So this was this 100% correlation of entanglement. And now the two parties, they are usually labeled Alice and Bob. So Alice wants to teleport a state to Bob, and then what they need is they have to share an entangled photon pair. So this comes from a source. For example, the photons travel through a fiber, go into Alice's lab, and the other one, the third photon, is into Bob's lab. And now Alice has prepared or also received via fiber from some other lab a photon of a certain state, C1. That's the first photon coming in, and this is now to be teleported. And how this works is, except of the entanglement, the second fundamental thing in this setup is this kind of measurement here. It's called a Bell state measurement. I won't go into the details, but what you do is you measure the photon 1 and 2 basically by this setup. So they are destroyed afterwards and are gone. They're absorbed by the detectors. And then the outcome, there is in this case 4 possible outcomes. This is then transferred via classical communication channel. There you basically just have, for example, internet connection from Alice to Bob's lab, and then you transfer the information of the outcome to Bob's lab. Bob has to adjust some measurement device according to the outcome, and then he can measure this entangled photon 3 in his lab, and either he can measure it and confirm that it has had really the same quantum state C1, or it can just leave out the measurement, of course, and just take it and be sure, 100% sure that if the teleportation, of course, has worked, but if the setup is like this, it will work. Then he can be sure that he has now the same quantum state as Alice before had. Without, and that's the point here, that photon 1 and photon 3 ever met. So you don't have to transfer photon 1 to Bob's lab. But via this entanglement, basically, you swap the state onto this photon, and this is then quantum teleportation. So I hope with this I could quickly give you at least an overview of how this setup works and how quantum teleportation works, and it was really demonstrated also with atoms and other particles. It really works out, and this is, I think, fascinating and really cool.